I want to talk about another example of chaos, but I just want to remind ourselves what the defining properties of chaos in a mathematical system are. Number one, it is aperiodic. That is, not periodic, which is the same thing as saying that it's irregular. The second point is that this irregularity and this aperiodicity is being produced by a completely deterministic system. And that means no noise, no external input. These systems are generating their own irregularity, and that's a topic we're going to get back to today. The third aspect is that it certainly has to stay bounded. It has to be confined within a bounded area. The fourth property that we saw was this extreme sensitivity to initial conditions. And this is the thing that's called the butterfly effect. And remember that the butterfly effect means that tiny, and I mean tiny, changes in the initial conditions can produce dramatic changes in the final state. And so therefore, detailed prediction of these systems is difficult, if not impossible. But that's also to be taken along with the other point that while detailed prediction is impossible, there are definitely, clearly, causes of chaos. And we can understand, if you want to call them mechanisms, I think that's also a good word, mechanisms of chaos, which are predictable and are understandable. And just to remind you what we did last time, which was the food chain where Z eats Y and Y eats X, we saw all of these properties exhibited by the food chain model. And I should really actually add a sixth, which is that there really is an attractor here. It's not a point attractor for equilibrium. It's not a limit cycle attractor for oscillation. It's a strange attractor, a third kind of attractor. So all of those are illustrated by the food chain model. And now I want to develop another example, sort of completely different, but it's going to have all of these properties. So this new example is a different kind of dynamical system. We have been looking in this entire course, we have been looking at functions that are continuous functions of time. If this is the shark population, we have S of t, and S of t is a continuous function showing the shark population at every single point in time. There's another kind of dynamical system, and it has dynamics too. And this new kind of dynamical system does not have a continuous time. It has what is called discrete time, meaning that the data come in discrete chunks. Here is data at time 1. Here is data at time 2. Here is data at time 3. And so the time axis is not a continuous function t, it's an integer value, what's so-called a discrete function, which is calling this f for a second. This is now f of n, where n is equal to 1, 2, 3, ... We can, if we like, connect these with straight lines, but the data comes in discrete times. What's an example of this? Well, there's a lot of examples of this. If we take your heartbeat interval, here's your electrocardiogram, and here is the interbeat interval 1, and here is the interbeat interval 2, and here is the interbeat interval 3. You'll see a case of this in a few minutes. So it's I1, and if we plot these, this is now the interbeat interval 1, interbeat interval 2, interbeat interval 3. What is interbeat interval 1.5? There is no interbeat interval 1.5. They come 1, 2, 3. Lots of additional cases. Stride lengths, the Dow Jones closing average today, the Dow Jones closing average tomorrow. Many, many examples of discrete time systems. So in discrete time systems, the dynamics takes a really simple form. In continuous time systems, we have the derivative s prime, and s prime is equal to yada, 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 and we have to make a differential equation, and we have to numerically solve that differential equation, and we have to deal with it using all the techniques that we've been developing. In a discrete time system, the dynamics is given by a very simple process in which we write xn plus 1, if x is the state variable, xn plus 1 is a function of xn, period. So here, we don't need differential equations. We don't need the machinery of differential equations. We don't need to let anything approach 0. We don't need to use any derivatives. It's just xn plus 1 is some function of the previous value, xn. Now, how do you get dynamics out of such a system? It's almost trivial. It's completely straightforward. First of all, you have to start, as always, with an initial condition, x0. Okay, what is x1? Well, x1 is going to be f of x0, whatever f is. What is x2? x2 is going to be f of x1, which is equal to f of x0. And you see where this is going. x3 is going to be equal to f of x2, which is equal to f of x0. And in general, xn equals f to the n of x0, where f to the n doesn't mean squared. f2 means f of f. f3 means f of f of f. And we are just going to, as they say, iterate this function again and again and again. Actually, we're going to iterate this function again and again and again. That's going to give us the dynamics. And so if we pick x0 here, this is going to be f of x0. And this is going to be f of x0, etc. And the dynamics are going to flow by applying f to the initial condition, and then applying f to the result of that, then applying f to the result of that. And it is a kind of a feedback system where x0 determines x1, which determines x2, which determines f of x2, which is x3, which determines f of x3, which is x4. And this dynamics will go wherever it goes. And we're going to develop methods right now to understand where it's going to go. So this new kind of dynamical system has a name. It's called a discrete-time dynamical system. There's lots of literature on it. And I want to look at a particularly simple example. So remember, we're looking for xn plus 1 equals f of xn. That's the definition of a discrete time dynamical system. And I want to pick a particularly simple form of f. In particular, I want to pick a linear function. Now, remember, we defined linear. A function f of x is linear if f of x plus y equals f of x plus f of y, and if f of ax equals f of x. But the bottom line of that, that's the abstract definition. The bottom line in a single variable is that if f is linear, it follows that f equals kx for some k. Those are the only linear functions of one variable. So we're talking about xn plus 1 equals k times xn. So we pick an initial condition x0, and x1 is k times x0, and xn plus 2 is, let's write it out. We have x0. The next point is k times x0. The next point is k times x0. The next point is k times k squared x0, which is k cubed x0, etc. So what does that dynamics look like? It depends on k. First example I want to take is where k is bigger than 1. For example, let's let k equal 1.1. So we pick an x0. Doesn't really matter what it is. And then x1, the next point, is 1.1 times x0. And then the next point after that is 1.21 times x0. And then the next point after that is 1.33 times x0. I keep multiplying the previous term by 1.1. What is that going to look like graphically? If I put n here, it doesn't really matter. This is 0. There's my x0. So if this is x0, the x1 is going to be 1.1 times x0. In other words, it's going to be bigger than x0. x2 is going to be bigger than x1. x3 is going to be bigger than x2. And in fact, this is going to trace out an exponentially growing curve with these data points right on it. That's an exponentially growing curve. It is going to go to positive infinity as n gets larger and larger and larger. Let's take another example. Let's try k less than 1. So k, for example, equal to 0.9. What is that going to look like? Well, we're going to pick an x0 again. It doesn't matter. Except I better pick an x0 higher up on the axis because I need that room. Because what is going to happen here is x1 is going to be less than x0. It's going to be 0.9 x0. x2 is going to be 0.81. 0.9 times 0.9 times x0. x3 is going to be 0.9 cubed times x0. And what that data is going to do is exponentially negatively approach 0. And again, the data points lie right on that curve. So here are two very simple examples of discrete time dynamical systems. And since they are dynamical systems, the concept of equilibrium point still makes sense in the discrete time context. And we can define an equilibrium point as xn plus 1 equals xn. Because if that's true, then the system truly is in equilibrium. Xn equals xn plus 1. It follows that xn plus 2 is equal to xn plus 1, and xn plus 3 is equal to xn plus 2, which is equal to xn. So the system doesn't change. It is indeed at an equilibrium point. Now, we learned in smooth time and continuous time differential equations, we learned that linear differential equations can have only one equilibrium point, and that equilibrium point could be stable or unstable. And exactly the same thing is true for a discrete time dynamical system. And again, for differential equations, if it's a linear differential equation, all the f's and g's are linear, then that equilibrium point must be at 0 or 0, 0 or 0, 0, 0. It has to be at the 0 for that system. Exactly the same thing is true here. And if we made a state space, which is X space, and that's 0, and we look at the first dynamical system, discrete time dynamical system for k greater than 1, well, if you started at a point here, your next point is here, and then your next point is here, and your next point is here, and you are going that way. Conversely, suppose we started at a negative x. Well, 1.1 times a negative x is an even more negative x. And that's an even more negative x. And so that's going that way. And therefore, what is this equilibrium point at 0? It's an unstable equilibrium point. Conversely, let's do the same thing for k less than 1. Here is our 0. If you started here in a positive x, your next x is smaller, your next x is smaller, your next x is smaller. Notice that the changes are getting smaller and smaller as we approach the equilibrium point. If you started here with a negative value, then 0.9 times the negative value is a less negative value, and so on. And then again, the changes get smaller and smaller as you approach the equilibrium point at 0. And what is that? That is, that's a stable EP, and this is an unstable EP. So linear systems are completely understandable. Their equilibrium point is at 0, and that is unstable if k is bigger than 0, and it's stable if k bigger than 1, and it's stable if k is less than 1.